A huge thanks to Brian for sponsoring this video.
Good morning, fellow mathematicians. Welcome back to video. So I woke up this morning with a real bad cold. Just suddenly happened. But I really wanted to create this week's video because I scrolled through my notes, my physical notes, and I noticed an integral which I haven't covered yet here on this channel, and it's a cool one. It's a really cool one. You should try it out for yourself and post your solution down there below. This is the sole reason why I'm still going through with it, even though I caught a cold, and I hope I'm going to perform kind of well. So try it out, give it a shot, and post your comments on there below what you got. By the way, this video is sponsored by the wonderful people over on Brain. More information at the end of the video. They provide a very cool service to the STEM community. Definitely make sure to watch till the end and check them out. Now we are going to dive right in. So the first thing I did in my notes back in the days, I only looked at it briefly because it's kind of clear what to do after the first few steps. If you have watched a few integration videos here on this channel, you might already see where this is going just because of the denominator down here. Now, first thing we are going to do is distribute the x into everything, and then we are going to break this integral up into two integrals using the linearity property of the integral operator. So this right here is going to turn into the integral from 0 to infinity of, and down here we have e to the x minus 1, and up here we have x times e to the negative x. And similarly, we have the integral from 0 to infinity of x divided by e to the x minus 1. And those terms only differ really by this exponential term that we have up here, but it makes a huge difference at the very end. Now, as mentioned a second ago, if you see this denominator down here, you might already get an idea of how to solve something like this. And this is the sole reason why I have broken everything up. What we are going to do is we are going to expand both fractions right here by e to the negative x over e to the negative x. In return, giving us a change of variable down here in the denominator, turning this into e to the x times e to the negative x is exactly 1 by the function equation of the exponential function, and then minus e to the negative x. And this is very good. This is very good. Let me write everything out and then hear me out for a second. This right here is going to turn into the integral from 0 to infinity of, and if we expand it by e to the negative x on both the numerator and denominator, we get e to the negative 2x up here. So x times e to the negative 2x divided by the term I just talked about, 1 minus e to the negative x dx, and kind of the same on the second integral, but just with x times e to the negative x up here. It's just a small difference. They are nearly the same, but not totally. 1 minus e to the negative x dx. Now, if we take a look at solely the denominator down here, or this fraction in general, 1 divided by 1 minus e to the negative x. Now you might notice on our interval of integration, so x strictly between 0 and positive infinity, this exponential term right here is always going to range between strictly 1 and 0. So it's never reaching 0 and it's never really reaching 1 either. So this right here is a positive integer between 0 and 1. And what is 1 divided by 1 minus, let's say, x, where x is between 0 and 1, where this is just the geometric series. And that's exactly the trick that we are going to use. We're going to turn this into the geometric series on both terms, and then we are going to play a bit of physicist because I'm too lazy to justify the dominated convergence theorem, for example. So let's go ahead and get started here. Let's get serious. So first one is from 0 to infinity of, we keep our first term how it is, or our numerator e to the negative 2x times x, and then multiply it by the geometric series where k is greater or equal to 0 up until infinity of, and our exponential term right here is exactly our argument, which is going to be raised by the kth power. So overall, by the exponential properties, this is going to turn into e to the negative k times x. And all of this integrate with respect to x. And similarly over here, we basically have the same thing, just with x times e to the negative x. I'm going to write it underneath here. So plus the integral from 0 to infinity of x times e to the negative x, and our geometric boy, once again, e to the negative kx integrate with respect to x. And this is what we got right now. And as mentioned a second ago, we are going to play physicist now. And without loss of generality, we are just going to interchange, it's a bit hand-wavy, obviously, our integral and our infinite series. It's a matter of changing limits. As every math YouTuber here, I'm too lazy to justify it. I already justified it in videos back then. So we're just going to do it, and we are going to pretend like it's going to work wonders, because it actually does, and it holds in like 99% of all cases, apart from the 1% of cases that mathematicians actually construct just to prove other physicists, engineers, and mathematicians wrong. So let's go ahead and get started, shall we? So this right here is going to turn, for now, that is a middle step, into, on the one hand, our infinite series, where it ranges over the integral from 0 to infinity of x times, and then we have those two terms combined, multiplied together, are going to turn exactly into e as the base. Then we have a negative sign and the x, and then we are going to have 2 plus k. Or k plus 2 really doesn't matter. And the same thing down here, but we obviously just have k plus 1. So we are going to end up with x times e to the negative, in parentheses, k plus 2 times x, integrate with respect to x, and then plus the infinite series, k greater or equal to 0 of the integral from 0 to infinity, x times e to the negative, k plus 1 x dx. And this is where we are right now. Pause the video if you couldn't follow along. It does make sense if you think about it for a second. Okay, next thing we are going to do, those should seem pretty familiar to you if you have watched the channel for a while by now. We're going to introduce a simple substitution now. We are going to let, respectively, k plus 2 times x or k plus 1 times x be equal to t on both integrals. So let's do just a simple substitution over on this part. So if we let t be equal to k plus 2 times x, this by implicitly differentiating turns into dt is equal to k plus 2 times dx, meaning overall we are going to get that dt divided by our k plus 2 term is equal to dx. I'm sorry, it's a bit cramped down here, but I hope you can see it. Or vice versa, we have the same thing with the k plus 1. If we now plug our substitution in, we obviously need to take a look at the upper and lower bounds. If we let x equal to 0, this whole term turns to 0, so the lower bound is 0 once again. If we let x go to infinity, k is a positive term. This quantity turns to positive infinity, which is t. So everything stays as it is. Very Gucci. So now, what this is going to end up after substitution is our infinite series, k greater or equal to 0, of our integral from 0 to infinity. I'm going to write out everything a bit bigger such that you can see better. Now, our x that we have here, we shall not forget it after substituting. X is the same as t divided by k plus 2. So this right here is t divided by k plus 2 times e to the negative, and by our substitution t, times the x divided by k plus 2, and plus the infinite series ranging over the integral from 0 to infinity of basically the same thing, just with a k plus 1. So t divided by k plus 1 times e to the negative t dt divided by k plus 1. So obviously k plus 1 and k plus 2 respectively are not with respect to our variable of integration, so we can drag it to the front, leaving us overall with two infinite series ranging over k plus 2 squared or k plus 1 squared. And all of this times the very same integral, which is going to resolve in t times e to the negative t dt. So let me write the last part out too real quick. K greater or equal to 0 of 1 divided by k plus 1 squared, integral from 0 to infinity of t times e to the negative t dt. And what you can do now for those integrals, the hardest part is already done. You can do integration by parts, where you differentiate your t and integrate your e to the negative t. It's going to go to 0 real quick, but if you got a sharp eye, this is a proof by looking very sharply at the blackboard for a few seconds. You might notice that this right here is just a gamma function of 2, which is the same as 1 factorial, which is the same as 1. Same thing over here. As mentioned before, you can do just a regular DI method, for example, and it's going to go to 0 really quick. And due to the limits, most of the stuff is just going to vanish or dominate in case of t going to a positive infinity and hence e to the negative t going to 0. Do it however you wish. Point being, what we are going to end up with is just the summation of those two series right here. K greater or equal to 0 of 1 divided by k plus 2 squared plus k greater or equal to 0 of 1 divided by k plus 1 squared. Now you can go about this in different ways. Now, you could write each and every term out. This is something that you could most certainly do and then see what you're going to get. You can do a change of variable in here or change of index, which is what I'm going to do now just to make my point a bit more clear. If you now say that we are going to let k start at 1, what you need to do is obviously you need to lower the index right here or our indexing function by 1. If we let it start at 1, then this right here must go over k plus 1, obviously. Just think about it for a second. We are just going to substitute basically our k by a new k plus 1, you could say. Okay, so this right here is going to turn into k plus 1 overall. No, we substitute by k minus 1, I'm sorry. And this right here is going to turn into just k squared overall. Now, the last thing I'm going to do is I'm going to write this term out now, and now it's ranging from 1 to infinity. And if I were to write this term out that we got here, let us just go ahead and get started. It starts with 1 divided by 2 squared. Then it goes on with 1 divided by 3 squared and so on. This term over here is the same as 1 divided by 1 squared plus 1 divided by 2 squared and so on. And this is where we do a simple indexing trick, you could say, or just a simple adding of a 0, because what we can do, we can actually trace this sum that we have right here or the series back to this one right here. If you compare those two, as mentioned a second ago, the only difference is that this series right here has a term of 1 divided by 1 squared at the very start. So if we were to add a plus 1 divided by 1 squared and subtract it once again, we are going to end up with this series that we have here exactly 2 times. But we also need to subtract the 1 that we got right here, such that it stays a true statement. So, plus our other summation that we are going to have, we are going to end up with those terms right here being exactly s once again. So overall, everything, this entire integral, is just going to turn out to be 2s minus 1. Now, what is our series that we have? Our series that we have 2 times is 1 divided by k squared, where k ranges from 1 to infinity. If you have watched the channel for a long time, you might know that this right here is just the Riemann zeta function of 2. So, overall, this is just a bit of basic knowledge. Plug in the Wolfram alpha, for example, it's going to spit you out. This is Riemann zeta of 2. So we got 2 times Riemann zeta of 2 minus 1. And Riemann zeta of 2, why do I know its value? It's because this right here is exactly the Basel problem, which yields pi squared over 6. So 2 times pi squared over 6 is the same as pi squared over 3 minus 1. So the solution to our integral is pi squared over 3 minus 1. At least this is what my notes say, but it's easy to get behind all of this. The only hard thing is actually getting the geometric series ansatz at the very start, and then you are basically good to go. And this is why I thought of this integral being very nice, because it yields a nice Riemann zeta value at the very end, which you might not expect after just basically splitting this integral up at the very start into 2 integrals. Did you get a solution? I'm gonna see down there in the comments below. So if you want to see more integrals, analysis, calculus, whatever it is in the STEM field and the land of mathematics, then the content of today's sponsor Brilliant might be the perfect fit for you. Now, when talking about Riemann zeta function, the first thing that probably comes to your mind is the Riemann hypothesis and the Millennium Prize problems. And I can't blame you for that. Pop culture mathematics is all over the place on the internet. And it gets covered a lot of times. But the thing with the Millennium Prize problems is that you need to study mathematics to get a basic understanding of those. At the very least, you need to study mathematics to really get behind those a tiny little bit. But this is where Brilliant actually could come in, because the Riemann zeta function and the Riemann hypothesis is actually one that you can kind of easily understand, at least the groundwork, when tackling everything with a few visualizations in the complex plane. And this is where Brilliant is extremely good at. Visualizations of mathematics, physics, chemistry problems. Whatever it is you might think about in the STEM field, Brilliant got you covered over on their website and app. With the nearly 70 interactive courses in all topics STEM, as mentioned before, be it the mathematics that we did today, physics, computer sciences, chemistry, Brilliant is the perfect source for you to learn something new on a daily basis on the go with their mobile app or at home on your computer. And their strongest suit are most certainly their visualizations and graphics that you can play around with. Not familiar with complex numbers? Not a problem. Take a look at the polar view of the complex numbers in R2 and you're going to notice that they are just arrows being spun around in the complex plane, for example. And Brilliant is so cool with their animations. You can just grab the arrow when it comes to vectors in general and just drag them around, see how the coordinates are going to change or points under transformations. Slide points around, see where they are going to land once you use a vector on those, and so on and so forth. The list goes on and on and on. Brilliant is just perfect when it comes to being a visual learner online. Or even if you are at school or at university, you can most certainly get a kick out of Brilliant by using their services. Don't trust me? Check it out for yourself. Free trial of amazing awesomeness using my link down there at the top of the description, brilliant.org/flammymaths, or the QR code somewhere up here in the corner. Check it out, the entire landscape of Brilliant for completely free. And if this feels like this could turn into a long-term relationship between you and the services, then why not make use of the link in its entirety and get 20% of an annual premium subscription. Brilliant is seriously the perfect source to learn something new on a daily basis. And I've been using their services for years by now. At school, to show to my students, or even in live streams here on this channel. They are just phenomenal. They provide a brilliant service, pun intended, to the STEM community everywhere over the world. They really do God's work, and I mean it when I say it. So check it out and support the channel this way, big time. I seriously can't talk anymore. It hurts so bad, my throat. But this integral was worth it. I really like it. Very cool result. And I hope you also got the solution right. If you were wondering, yes, this right here is trash. Oh, goodness. Goodness gracious me. Gotta end this video now on a good note. Oh yeah, it's probably Sunday by now, but why not make it about Friday? 7 AM, waking up in the morning, gotta get dressed, gotta go downstairs, gotta have my bowl, gotta have cereal, seeing everything, the time is going, taking on and on, everybody's rushing. See ya!